Hello everybody, and welcome to our webinar in which we will be comparing common criteria with the DO-356A standard. Thank you for joining us today. I'm Mark Tootle, your host and the Regional Account Manager for UK, US and Canada here at SYSGO. The webinar will be delivered by my colleague Dr. Oliver Coulert. If you have any questions after we finish, please feel free to reach out to Oliver, myself or your account manager, and we will ensure we get them answered as quickly as possible. And now may I hand over to Oliver for him to introduce himself and start the webinar. Oliver, over to you, sir.
Hello and good afternoon. My name is Oliver Coulert. I'm working as a technical product marketing manager at SYSGO. And today I will talk about DO-356A standard, which is relatively new from 2018, and how it can be covered by means of a IT standard, the Common Criteria Evaluation. So just to give you a quick overview about what are you expecting today. We are currently at the introduction. Then I will introduce you into those two standards. Then we will talk about security assurance objectives, which are the, let's say, most important topic of the new standard. We will talk about risk assessment, refutation analysis, and finally about the security architecture as described within the DO-356A. So who are we? We are actually the number one in Europe for operating systems, for embedded systems, which require safe and secure technologies. SYSGO is almost 30 years old, and since 2012, we are members of the Thales Group. We have two main products. The first one is the PICOS operating system, and it is a hard real-time operating system, which at the same time is able to act as a virtualization guest operating system. It is a type 1 hypervisor and it allows to host real-time operating systems and non-real-time operating system at the same time by still keeping the real-time attributes of the real-time operating system, which is running in parallel. In addition to that, we have Avionics, which is an embedded Linux distribution, which is targeted for security and safety as well. And Avionics can run as a guest operating system on top of PICOS as well as standalone. Okay, that's for SYSGO. Let's start with the DO-356A standard. This standard comes because of the demand of security as modern aircraft are connected with the infotainment system, with ground stations and aircrafts amongst itself. Connectivity has become a major issue also in avionics. Until now, the DO-178PC and additional standards handled mostly safety and had a little glimpse view on security, but not deep enough. With the DO-326A standard, which is a little bit older, about 8 years, the cybersecurity was covered directly. And with the DO-556A standard, we now have a practical guide how to follow the security standards as proposed by the DO-326A standard. So the DO-326A is mostly about processes, and the DO-356A is about how to practically implement security within airborne systems. And of course, the standard follows the processes as shown in the DO-326A. So the content of the standard is, it starts with regulatory considerations in section 2. This talk will mainly focus on the security assurance objectives, which are basically kind of requirements how to implement and plan the topics to make sure that the aircraft or the system is compatible to the 326A standard. These are actually handled in section 4, but we will first start with those. One major topic of the security assurance is the risk assessment, and we will have a look at it. This is actually considered in section 3 of the standard. And many of the concrete guidelines are not in the main text of the standard, but instead in the appendix. So very often we will take a detour into the appendix. Finally, we will have a look at the security architecture as proposed by the DO-356 standard. So let's start with the security assurance and have a glimpse detour to the common criteria before. So this is a universal security standard, which is used in many industry, mostly the IT sector. It is an attempt to make the security of IT measurable and comparable against systems. And it covers the whole development processes like architecture, development, verification, validation, and testing. Most of the security targets, which are the, let's say, introductional chapter of a common criteria evaluation, is published so that you can read it. The security target and the perfection profile of PICOS is available on demand. So there are several roles in the common criteria evaluation, which is a little bit different to existing safety standards like DO-158. So we have the official certification body, we have the developer, and in addition, we have the security evaluation facility, which is an independent facility which provides the evidence to the certification body. So this is a little bit different to what we know from safety standards. So the main topic of the DO-356A is intentional unauthorized electronic interaction. What does this mean? So the scope of the standard only covers events which originate from a human and are intentional. The events must be unauthorized, they are electronic, and they come by some kind of electronic interactions, like attacking the system via digital interfaces such as CAN or AFDX or Ethernet. Just to make sure, physical interaction is not part or not covered by DO-568 standard. So the security assurance objectives are requirements that measure whether the assurance performs as intended. The assurance should make sure that the system is free of known exploitable vulnerabilities. Well, this only, of course, 100% coverage can only be assured in a perfect world, of course. It covers the entire development process, beginning at the architecture, the design, implementation, and the testing, of course. It covers intentional unauthorized electronic interaction topics only, and we are talking about security for safety. That means that the standard does not cover the protection of access to credit card numbers in cabin infotainment system, but of course the protection of the firmware of the cabin pressure sensor is irrelevant, as failure of this one may result in a catastrophic event. The standard actually has or groups the security assurance objectives into two kinds. The first one are security specifics, which means they are totally new. These objectives explicitly come in the new standard and are requirements to security only. We'll try to cover those objectives by means of common criteria classes. This is handled in section 4.1 of the standard. The second kind of security objectives are security development objectives, and these are basically the same as we know from DO-178C and other safety standards. So this covers actually the development. These requirements, which are listed in the standard, come in two ways. The first one are regular, which means there is nothing to add to existing safety standards. It's all the same. And they are partly augmented, which means some of the objectives listed here have additional security considerations. If possible, we try to cover those additional augmented topics by means of common criteria classes as well. These are listed in section 4.2. So the security assurance objectives are a long list, which needs actually to be done. They relies on the security assurance level. So in case you have a very low level, there are not that many assurances to fulfill. If you have the highest level, then all the security assurance objectives needs to be met. During this talk, we are assuming that you are trying to achieve the highest level, 3, which means all security assurance objectives are mandatory. So what needs to be given for given security assurance levels? Well, if you look into the index, there's a whole list of all the security assurance objectives, and there's a list of the security assurance level, and there you can see whether an objective is required or not. This is listed in Appendix A.1. This is actually one of the most important tables in the document. So how do the common criteria classes now come into play? Actually, there is a second list in the standard. It's in Appendix B1.1, and it lists all the security objectives again. And it shows whether the objectives are already covered by existing safety standards and whether you can cover them by common criteria related classes. So we see what, for example, 01.1 is actually covered by the security problem definition of the common criteria classes, but for example, the threat condition is not. So let's start with the security scope. It is the first step of the risk assessment, and the definition of the security scope first starts with the definition of the assets which needs to be protected. Then you define the security parameter, which basically is a catalog of all interfaces to the external systems or persons from the asset. It lists the security environment, which are all the organizations, persons, external systems, or even possible attacker would be able to communicate with the assets via the security parameter. So here's the asset. We are following an example of the standard, which talks about the firmware of a pressure sensor firmware. It is connected to the security environment by means of a interface such as ARINC 664 or CAN interface. The security parameter is the catalog of interfaces with external systems or persons. When talking about the security scopes, we always have to consider the security environment because not everybody in the security environment may be an attacker. So for example, the maintenance crew may officially be able to exchange the firmware. And we have to make sure that the maintenance crew can do its work. So in terms of common criteria, the security scope is actually called security problem definition. And the terminology of common criteria is a little bit different of DO-356A. So actually the aircraft or system to be certified is called target of evaluation within common criteria. The security scope is called security problem definition as it keeps its name. The security parameter has the name theory boundary, and the security environment is called operational environment. A part of that, this is pretty similar. And after we've defined the security scope, we will now analyze the risk. So first, we start with identifying the threat conditions. Then we identify so-called threat scenarios. From these threat scenarios, we characterize security measures in order to reduce the risks that is introduced by the threat scenarios. Sometimes if you introduce new security measures, they change the system and thereby new threat scenarios may arise, which means after the characterization of the security measures, you have to identify and refine the threat scenarios again. After that, you can evaluate the level of threat. This is very similar to the methodology of common criteria. Here, threat condition is called just threat. For the threat scenario, there is no real counterpart in the common criteria, but we will soon see that this more or less is a grouping element. The threat source is called attacker. The attack path remains its name, and security are called countermeasures in common criteria. The whole risk assessment is handled in the security target of the common criteria. we come to the threat scenario right now. So common criteria, as we can see, are pretty close to DO-356A, but there is something to consider. While identifying the threat conditions, we always have to keep in mind that DO-356A is about security for safety. That means on aircraft level, we start with the existing failure conditions we already know from the safety standard threat evaluations. So we start with existing failure conditions. We will soon come to an example and derive the threat conditions from those which have the same effect. So, for example, a failure condition which comes from the safety world would be the loss of the pressure for crew and passenger, which of course is a catastrophic event because people may die. So there is a threat condition which we can derive from these failure condition, and it comes from controller corruption of the firmware of the pressure system. You can derive multiple threat conditions from one failure condition. The entire example can be seen on the appendix DO-3 of the entire example. So you start with the evaluation of existing failure conditions, identify new threat conditions with the same effect from this. Afterwards, you go over the entire systems and identify additional threat conditions which come from loss of additional security attributes. This needs to be executed for each asset you want to protect in the system or in the airplane. Threat scenarios are introduced with the DO-356A, and they basically have a unique ID, and they just group the assets, the threat conditions, the threat sources, the attack vector and the path, and the security measures which have been defined to counterfight the threat conditions within the threat scenarios. All these topics are actually covered by common criteria. There's one which, of course, cannot be covered by common criteria, and this is the effect of the air condition and crew and passengers. So this needs to be tailored in addition to the common criteria classes you already may have. So here's an example of the threat scenario. On the right, you see the threat conditions which are being covered. You see the security measures which you define in order to counterfight the threat conditions. And you see the threat scenario here. You see the threat sources and the attack vector and the attack path. So the security measures in order to counterfight against a threat condition, for example, would be that you only allow data exchange via Ethernet and CAN interface, then the aircraft is set to maintenance mode. In other words, the maintenance crew may only exchange the firmware, then the whole plane is in maintenance mode. So this may not happen during flight, and this is one security measure to make sure that an attacker cannot corrupt the firmware during flight. The security measures need to be characterized, which means they get a description, they describe the protected assets, the type of the effect, and the dependencies. While doing so, you make a common mode analysis in order to make sure that all the security measures are independent from each other. So one failure on one security measure does not have an impact on the other one. They need to implement in a diverse way, and they should be isolated from each other. Once you've done the threat scenario evaluation, we now come to the level of threat evaluation. So typically we have 5 levels in the scale. This is to be able to compare among systems. Here, it is very important to understand that in the threat evaluation in safety, you would talk about probability. In case of security, it is not the case, because if it's intentional, there is no probability that an attacker would attack the plane. He can do it at any time, and since it's intentional, you cannot deal with probabilities. Instead, what you evaluate here are the preparation means, which means how much is the effort for the attacker to prepare an attack, what kind of data can he get? So is the documentation of the airplane public? or is it confidential? So if it's confidential, or if it's even a bespoke system, it's way much harder to attack the system than it's public. The window of opportunity, when does actually have the attacker time to attack the system? So if it's only during maintenance mode, there's almost no way that the attacker can attack the airplane. And finally, the execution means, what does the attacker mean to attack the plane? Does he need special hardware? Does he need to connect to some kind of network? And how can this be observed? The standards main text actually does not provide any method how to actually make an estimation of the threat scale, but the Appendix E staff does, and this is compliant to common criteria. Actually, then in Appendix F, there is another way, but we will focus on the common criteria compliant method of evaluating the level of threat. Now, is the risk acceptable? Finally, you have the level of threat here. You have level of threat on the left side, and you have the severity of the threat condition. And then in this matrix, you can look up whether your current security measures are enough to secure the plane. If not, you have to take another round in the risk evaluation. Finally, risk consistency. The level of threat evaluation of an airplane is always preliminary, and it often needs to be adjusted by low-level systems. So if you have a very high system like the entire airplane and you have evaluated the level to be moderated, there may be subsystems, and if a subsystem has a higher level of the level before, then this threat level evaluation actually walks up in the tree. And if you're unlucky, a low level with very high risk evaluation may change the risk assessment of the entire plane. So we've talked about risk assessment now, which is the largest issue introduced by DO-356A. But what else? Most of this can be covered off means of common criteria, but some tailoring is required. What is remaining? Well, DO-356A talks about vulnerability identification and handling. This is covered by vulnerability assessment of the common criteria classes. It talks about refutation analysis and testing. We will come to that very soon. In addition, security guidance is required by DO-565A. And this security guidance basically is a handbook for the user which shows how the user system should be used in order to ensure safety. For some unknown reasons, the standard does not list any common criteria classes in the appendix, but actually there is some which comes from common criteria, and it's the operational user guidance. The same is valid for continued security, which describes how during the life cycle of the airplane security should be ensured. For example, if during the lifetime new vulnerabilities arise, then the continuity security describes how the developer will handle those situations. Actually, here again, the standard does not list any common criteria classes, but there are some, and these are flaw remediations. So, also not listed in the standard, these two things are recommended by SYSGO because you can cover security guidance by operational user guidance, and you can cover continuous security by flaw remediation. We now come to refutation analysis, which is something new, and it is introduced by DO-565A. It is demonstrating the absence of information security problems, and the requirements here are typically formulated in the negative context, like shall not. Refutation and requirement-based testing are different by nature. While requirement testing is something we know from safety standards, when you do refutation testing, you have to go into the perspective of the attacker. An example for a refutation requirement would be the system should be robust against invalid input over an Ethernet link. Well, that's a very, let's say, strong requirement. How would you able to test this? Actually, you cannot do it because you need a high volume of test cases and you will never be able to test all input vectors, which means you will never be able to test all possibilities that can be sent via an Ethernet links. But you can do representative testing like penetrating testing, fuzzing. You can do a static code analysis. You can do dynamic code analysis. Well, formal proof would also be possible, but we all know that a complete verification is a whole lot of effort and you can do it only for very small systems. Actually, these are the same test methods that are used for vulnerability testing. That means we can understand refutation analysis as some kind of analysis and refinement of the vulnerability tests. And these are actually covered by common criteria classes. So if you look back into those roles here, it is actually these guys here which are planning and executing the vulnerabilities. And the planning of the vulnerability test can be somehow interpreted as the analysis of what needs to be done. So which means when these guys are actually planning those tests, you can get a document from them which describes why they do this test, and this can be treated as the refutation analysis. This is a recommendation from SYSGO, of course. And that's it for the security-specific assurance objectives. Let's take a glimpse look into the remaining one. These are the security development objectives, and these are mostly known from safety processes. And as I've talked before, there are regular ones, which means there's no difference to what we know from safety standards. And there are augmented requirements. These have additional security considerations. And if possible, we will take common criteria classes into consideration. So let's see what actually needs to be done here. So these are derived requirements, security measure, and so on. All these things which are required are actually covered already by safety standards, which we all know. But of course, you need to do those things for the new security requirements. In addition to that, you need now to prove software authenticity and integrity. That means that the system upon startup actually sees whether the firmware is valid in terms of security. And this usually can be done by terms of a digital signature, for example. Before the DO-356A standards, this was actually not required. And now you make sure that the system actually has a digital signature, making sure that the firmware has not been changed by an unauthorized developer. In addition to that, the configuration management tool, for example, your Git system, which you've been used before and which was required by safety standards, okay, and right now needs access control policies, which means that your developers need a username and password to log in. Well, this sounds a little bit clear, but it's required now by the new standard. In addition to that, all the tools which are used during the development now needs to be checked for their vulnerabilities, just to make sure that an outside attacker cannot have an impact or change your development tools. This is also new and came by the new DO-356A standard. So we are now done with refutation analysis and the security assurance objectives. We will now have a glimpse look into the security architecture as required by DO-358 standard. You have to make sure that your architecture cannot be bypassed by any way, that all your security measures and assets are not exposed and cannot be tampered or bypassed by an attacker. You have to make sure that your security measures are independent from each other, that they are implemented in a diverse way, and that they are isolated from each other. And finally, any attack should be detected and recovered by the system. But here comes an important difference to usual security mechanisms and recovery. because we are talking about security for safety, we always have to make sure that our intrusion detection system does not shut down any communication lines which are necessary for the pilot to fly the plane. For example, if you detect an attack and would shut down the AFDX line, the pilot would no longer be able to fly the plane. So this should not be happen. So if you plan the detection and recovery systems, always make sure that fail-safe goes over fail-secure, which means that the system goes into a safe mode in terms of safety and not in fail-secure way in terms of security. So safety is more important than security in an airplane. So finally, the aircraft security should be based upon a layered protection, which means that your security measures are consensitive and that there are multiple security measures. These security measures should employ independence, diversity, and isolations. And you should avoid to run your security measures in a monolithic OS with many lines of code, which could be easy to attack. Instead, use virtualization techniques by means for a separation kernel, for example. You always should make sure that you use a hardened and certified operating system. The preference is on real-time capabilities to support safety requirements, and partitioning allows the implementation of intrusion detection systems without that these intrusion detection systems would interference with safety critical applications. Of course, one of the examples would be to use a microkernel which comes from PICOS, from SYSGO, because we are certified according to DO-356A. We have a security evaluation from the BSI, and it's according to common criteria ERL level 3+. We provide separation, isolation, mixed criticality, virtualization, and we have hard real-time. Now I want to conclude my talk. The DO-356A standard introduces new security assurance objectives in order to demonstrate the evidence of airworthiness. These come by security-specific assurances. These are mostly covered by common criteria. Additional work needs to be done for risk assessment and refutation analysis. And we also need to cover the security development assurance, which we mostly known from safety practices. These are also the augmented development assurance are mostly covered by common criteria. I've quickly showed the security architecture as introduced by DO-356A. The defense in depth architecture, we've shown how you can implement independence, diversity, and isolation by means of a separation kernel. Basically, that's it. Thank you very much. And I will give back to Mark then.
Thank you, everybody. All I can say is thank you for your attendance. Thank you for your time. Feel free to reach out to us at sales@sysgo.com, or indeed, if you know your account manager, feel free to reach out to him or her, and we will try to answer any questions you have. And Oliver, we have a thank you as well. So thank you, Oliver, for your work. We can call a close on this presentation, but thank you everyone for your time and your attendance.